Well, that was a little touch of algebra in our last section of Chapter 7. In Chapter 8, again, we're not doing many of the sections, but it deals with graphs, functions, and systems of equations. Again, we're only going to look at functions a little bit, and then later exponential and logarithmic functions. And again, the nice part of it is that you can use your notes. So taking good notes and following along with what we're doing is a really useful thing here. So we're going to be doing topic 8.4 and then later 8.6. But I thought this was nice. The day my algebra class finally made sense. Well, if you read through this in your textbook, it talks about a student who didn't see a lot of connection to what he was doing in his math classes to what was going on in the real world about him. But then one day his teacher was talking about ordered pairs, graphs, function lines, slope, intercepts, and other things. And he had gone to the filling station to fill up his tank. And then he noticed the price of gas, and this was sometimes in the past. We're in good shape right now. Although when I was a kid, it was like 25 cents a gallon. But anyway, he saw this, and then as the wheels started to spin, he took some pictures, and he realized that the gallons of gas he was filling his tank with, and then the price that was showing up on the pump, sort of made interesting data. So he took some pictures of the pump and then wrote the data down. And here, this column would be number of gallons, and this column would be the sales price. And if he were to take this data and plot it on a graph, he would end up with something like this. And this is the section we just finished. That's why I wanted to show you this, because what is being shown here is a direct relationship. Y equals kx. And this type of relationship produces a straight line, where y here is the price, k is the cost per gallon that we said was $3 and some cents. I forget now. And x was the number of gallons. And direct variation, and if we were to do graphing, this is a illustrative method of showing your data, which is what graphs do. But we're going to jump now into the topic we're going to deal with, which is 8.4, an introduction to functions. Now, I went over that first part of chapter 8 because they use it here, and in a sense, the relationship of the number of gallons to its price creates what we call an ordered pair, or an item of data. And again, on a graph, the x-axis is this one, and the y-axis is this one. And as we saw the price of gas, you had a line that was a direct variation. So one of the things we're going to do is look at what is the definition of a function, and then a special case, a relation. Now, any two numbers of data that are related create a relation. So that's what a relation is. Somehow the numbers are connected. And these numbers, when they are plotted on a graph, makes points on a graph. And you can actually plot those points and then connect them with a straight line. And there's an infinite number of points along that line. Now there is a case, though, what makes a function? And I'll give you that definition and we'll see it as we go. Well, in a function, the x unit in a relation is only used once. So if this were a 1 and then a 2 and a 3, they're only used once. That would be what a function is. So let's continue. And that function, as we had described earlier, can be given as y equals kx, where k was the price per gallon, x was the number of gallons, and y was the end price. And as we build vocabulary, the x member of the ordered pair is the independent variable, and the y member of the ordered pair is the dependent variable. Now it also gives rise to some other vocabulary words that when we have an x and y, the x element of an ordered pair is the domain, and the y element is the range. Now if we put x and y alphabetically, that's the way they are, and if we put d and r alphabetically, you see they line up. So a way to remember them, which is which. So x comes before y and d comes before r. Okay, we're going to now give an official definition of function. And a simplified way of thinking it, I like to use this, it's very short, that the x element, that is your domain element, whatever it happens to be, is used only once in a series of relations. If you have a 1, it's used once. A 2, used once. But if you have a 1 and then another 1 used, it's used more than once, it's not a function. And that's what they're saying here. Exactly one value. Okay, let's go on to what is called function note. So we'll use what is here. When a function f is defined with a rule or an equation using x and y for the independent and dependent variables, we say that y is a function of x. To emphasize that y, which is the dependent element, is dependent on the x element, which is the independent element. And we could say y equals the function of x. Now, another thing we're going to see very often is that y and the symbol for function can be interchanged. So if we wanted to write this, which is a y function, we could exchange the y with the function symbol f of x equals that. And that's what they're showing you here. So often we can substitute the f of x for the y, or y for the f of x. Now, how do you work these out when they ask you to do some computation? Now, had we spent time doing some of the earlier lessons that are not in our curriculum, I would have suggested using what is called a T-chart, where it looks like a T, and then on this side you put the x, and on this side you put the y. So they're asking us to, in this example, if we replace the x with a 2, so we'll put a 2 under the x column, and remember we could replace the y with f of x. What would be, if this is your independent variable, what would be your dependent variable? So we would take the 2, put it where the x is, and we get 3 times 2 minus 5. So we replace the x with the 2. 6 minus 5 is 1. So our y value, or our function value when x is 2, is a 1. So it's written this way sometime. Again, I like the use of a T-chart to help you keep it orderly. So again, they're giving us a little reinforcement of our vocabulary here. The name of the function right there, that could be replaced with a y. And then this is our defining expression. This is our function here. So we're going to input a value for x and then get something that comes out of that. So here we see in example 1, they're going to give us 3 values for x, and we want to know what do they come out as. Well, for this, I would suggest you set up a T-chart, and now you're going to place your values of x into the T-chart. If x is 0, if x is 1, if x is 3. And your equation is a negative 2x plus 3. Well, if we substitute a 0 there, that's going to be 0 plus 3. So this value would be a 3. If we put a 1 there, that is negative 2 times 1 is negative 2 plus 3. This will be a 1. And again, if we put a 3 there, negative 2 times 3 is a negative 6 plus 3 is a negative 3. And this way you have the work to support and a way to illustrate your results in a neat and orderly way. This is what you want to work on. In letter D, they're not giving you an x value, they're giving you the y value. Remember, this is y equals 7. So in our T-chart, we put a value as the f of x being 7. So we put that in our equation where the y is. What will x be? Well, we're going to subtract 3 from both sides. That will give us a 4 equals 2x, a negative 2x. Or we just transpose the 3. On this side it becomes a negative 3. Negative 3 plus 7 is 4. And now to get x by itself, we divide both sides by a negative 2. So we get x then is going to be a negative 2. And if you take the 3 that we had in the previous slide, along with this one, and just put them in ordered pairs, those would be your ordered pairs. And if you put them in a graph, they would make a line that looks a little bit like that. And these would be along the line, your ordered pairs. And we see that here. Okay, what is a linear function? Well, a linear function as we saw in the graph, the beginning of this chapter was a straight line. And that is what linear means, that these functions, in this case, would be straight line functions. Okay? Now, they're saying, suppose you just bought the gas, then your line would look like so. But suppose you had your car washed. What would be your end price? And it costs $4 for a quick car wash. Well, this changes your original relationship to this 310 times X, but now plus $4. So this new graph would, and if this is 0 and then it was 1, 2, 3, 4, then the $4 would be here and your line would start up the graph because of this added charge of $4. Now, I don't know if you have this. Again, if we had studied some of the other areas, we'd see that this equation is now in this form of slope-intercept, where m is the general slope of the line, and the b is where the line crosses or touches, in this case, the y-axis. B is called the Y-intercept. So it's going to cross or touch it at 4. Here, there wasn't any Y-intercept, so it touched it at 0, which is what is right there at the beginning. So, again, this type of relationship where they are straight lines are a linear function. And again, we didn't cover some of this. We're giving you a little bit of background, and hopefully you're taking notes. So m, write this here, is the slope, and the b is the y-intercept. And the y-intercept b is where this touches the y-axis. We're going to use that a little later too in what we go over. Now, there's a lot of interconnection between what we did earlier, y equals mx plus b, which is the slope-intercept form, where m is the slope and b is your y-intercept. And this form here for linear function, we're changing the y to f of x, and we're using the a as the slope. And then we have our y-intercept. Now, the y-intercept, by the way, if you ever see it as an ordered pair, is written in this form, 0, comma, b. So the x value would be a 0, because that, if you had one like 0, comma, 4, 0 is our x value, and then it would go through or have a point on the y-axis at b. That's why that's called the y-intercept. So this formula gets its name from it containing the slope and the y-intercept, slope-intercept form. And we often add linear of the linear equation in two variables, x and y, which are your ordered pairs. Now in example 2, they're going to ask us to graph linear functions. So here in this first example, letter A, this is written in slope-intercept form. So -2 would be our slope, and a +3 would be our y-intercept. Now, below they're going to show you a way to get various points, but I'm also going to show you a way to graph this using a special technique. And it looks like this. Now I'm making this little graph here, and unfortunately I don't have a clear space because I've used this up over here. So what's our y-intercept here? Well, we said it's going to cross the y-axis here at 3. So we put a dot at 3. We know it's going to cross the axis there. Now as we look at our slope is a negative 2 over 1. Even though they're not showing the 1, every number is over 1. Now slope, they're going to tell us here shortly, is a ratio that we had earlier of y units over x units. And y is up, so we call that run. And x is across. How about, if I'm a little more careful here, up is rise. Sorry about that. And across is run. Okay, so a ratio of a negative 2 over 1, y over x, rise over run. So from this point of intercept, where it crosses the y-axis, we're going to have, and I like to do it this way. There are other ways to do it, but if it's negative, I'm going to do my x value first, which is a 1. I'm going to go over 1 mentally as I put this in MATLAB, and then I'm going to go up 2, 1, 2. So I put a dot there with my tool, put another dot there, and then get my line tool, and then the line forms. And then this is the graph of this particular example. Now below I'm going to show you the other way of doing it, but I think this is a good way of doing it and not having to know too many things. You plot the y-intercept, and then you plot your slope. And it'll take some practice. All right, let's go up. And before we go up, I should mention the second equation here. This is a form of y equals b. And we know that b is the y-intercept. There is no x value. X values happen to be 0. So what we do in something like this is a special equation of a horizontal line going through b, which is the y-intercept. So let's take a look at it. Now another general way of plotting this, instead of using the slope-intercept, the y-intercept, and the slope, we could put a t-chart where we put various values in there. And once we get these values, which they have here, you plot those individual points. But again, a much easier way, I think, is you're going to put a dot on your y-intercept, and you're going to go over 1, up 2. Over 1, up 2 if you wanted more points. Now you could have gone down 2 over 1, down 2 over 1, down 2 over 1, and eventually you would get all of these points as well. Now the special case for this one, where it's f of x equals 3, or y equals 3, we said this was a horizontal line. So you put a dot on 3, and then a dot anywhere else, and your horizontal line forms. Now an interesting thing about horizontal lines, just to give you some background, the slope of all horizontal lines is 0. Now lines that go this way are negative slope, and lines that go this way are positive slope. Some background. So starts high, goes down, negative slope. Starts low, goes up, positive slope. Horizontal line, zero slope. Now another thing they're asking about this is, what is the domain for each of these? And what is the range? Well, remember, domain are your x values. So theoretically, in time, this is going to head out to that left direction. And what is way out there on your x axis? And the answer is negative infinity. Now this eventually will go out this way too, slowly, but eventually. And what's way out here? Well, positive infinity. So for your domain, when we put in what is called interval notation, it goes from negative infinity, comma, to positive infinity. And for infinity, we always use a parenthesis. Now, for the range, this eventually is going to go up this way and down that way for our y values. And again, it's coming from down here, negative infinity, and going to positive infinity up there. So it's the same for both. And that would be true for negative slope and positive slope. Now, how about for this horizontal line here? What will be our domain? Well, here definitely it's going off to negative infinity, and here to positive infinity. But how about our range? The range is only at one spot, at 3. So we write the range as, in a bracket now, we put a 3 in there, and that's our range. Only that. Now I see in our textbook they're using braces for the 3. I would use a bracket. So I'm not sure why they did it that way, but that's not the way I would do it. Okay. So we mention again, this is a special function where y equals b. This is a horizontal line. And we mentioned also the slope is 0 here. Right up there. Now they're giving us a linear model where we are going to analyze cost, revenue, and profit. Well, let's give a little background on this. And it's helpful because they've used the letters that they're talking about. So C is for cost. And what does cost involve? Well, usually you're going to make a certain number of products, and that's your X. And to make a particular product, let's say a batch of stationery, you're going to need paper. So for each packet of stationery, you need so many pieces of paper. So to buy that paper to produce that particular packet is going to cost something every time you make that single unit. But also involved in the production of that stationery is to have some sort of printing machine. And this printing machine is a capital expense that you need to purchase, but you can use over many, many, many times. So this is sort of like we call a fixed cost. And that's your capital investment. Now, to make a particular packet, you need to have paper. And that's your individual cost of producing a particular item, plus these fixed costs. So that's what this refers to. Now, when you sell an item, it brings in money, and that's called revenue. That's what the R stands for. Now, you're going to sell these packets of stationery, and you're going to figure out some kind of cost of the selling price of that packet so that you can eventually make some money. So that's what the revenue equation looks like, what you're going to sell each packet for. This is amount of dollars, and of course this is amount of dollars here too, or some kind of cost to make the paper, fixed cost. Here, this is what's coming in. This is going out. This is what's coming in. Now eventually, if you take your revenue, this is your money coming in, and subtract your cost from that, you have to put this in parentheses, which will be, you can write it this way, because it's usually two things. You have to put both in parentheses. So eventually you'll get something subtracted from all of this. This gives you your profit. So, express the cost as a function of X and the number of DVDs produced and sold. Well, here the company places an ad. The cost of the ad is this. Each DVD costs $20 to produce. So for this, it's going to be cost is $20 to produce, and then you have to pay for each DVD plus the ad to sell them is $100. So you have to pay that $100. Okay. Now the sale, when they sell a disc, they're going to pay, or the selling price is $24. So revenue is going to equal 24x. So for every DVD you sell, you get $24. So express that. Okay, we got that. Now, when will the company break even? Well, remember we said we could substitute a Y for this and a Y for this. So, again, a Y here and a Y here. So we can say that this then equals this. So our formula would be 20x plus 100 equals 24x. And this would be our cost. And this would be what we take in, the selling price. And we're looking how many of these units in order to break even. All right, so we substitute here, we subtract 20 from both sides, and we get 4x equals 100. Now we divide both sides by 4, and we get x equals 25. Now if we were to graph that, and we've used up all our clear space here, but the blue line represents your revenue function. You start at 0, and as you sell them for $24, it looks like so. And your cost, remember you had that $100 that you had to make up, so it brought you up there. That was your fixed cost. And then it went up. And then right there at some point, the lines crossed one another. So this was the break-even point when you sell 25 DVDs. After that, you start to make a profit. And they asked to graph it, so we did that. We did all of this. And of course, their graph's a little more detailed. And right there is the point where they break even. That is, they have to sell 25 DVDs, and then anything above that, they start to make a profit. Anything below that, they start to have, or they would have, a loss. Now, in this example, they'd like us to model tuition cost, where in this column will be the years, and we'll say our first year was when we started, and that would be our 0 year, and then 1 year after each of these dates, and then this was the cost. So we're asked to make a graph of this, and they do have a graph here. And then we're asked to find an equation of that graph so that in a future time we might be able to predict what it would cost. All right, this is somewhat of a challenging problem. So what we would do is we would take our data from, let's say, the first and last year, and that would be, this is our Y value for the first year, our X value from the first year, and then your Y value from the fourth year, and your X value from the fourth year. And remember, we said slope was a ratio of Y over X. So we find that our slope from this is this, and when we put it in decimal form is this. So we can then put this in slope-intercept form. And notice now we have Y, or we could put it in function also. Our slope is 11925 times X plus, what was it that first year? What's our B value? Well, they give it to us right here. Our B value is 2787. So there's our equation. So what year do we want? Well, we want the year 2009, I believe, which is 5 years into the program. So we're going to put a 5 there, where the X is. Multiply this through, add it to this, and that should be our prediction for the 5th year. And if this trend holds true, we could predict any number of years in the future by putting an X value, which is the year value, in there, because this is how much it's going to go up each year. So looking at this, community colleges aren't too bad. I know when I went to Southern years ago, my initial tuition in 1954 was $10 a semester. Wow. By the time I left in 1958, the tuition had gone up to $100. And it used to be that if you're on the dean's list, you would get your tuition back. I got mine back a number of years. It wasn't too much, but it was nice. All right. And to finish that up, for 1914, I guess there's 2014, they're starting in 2009. It was 5 years. So you put the 5 where the X is, and this is the approximate tuition perhaps in that year. Now let me give you the slope formula, and this was covered again in a part that we hadn't done, so you would need to have this. This is the slope when you have two coordinates, two sets of coordinates, and you designate one as the sub 2's and one set as the sub y's, and you just substitute it in there, which is what they were showing you above. Right above there, we don't see part of it there. And then they use the f of x equals mx plus b, and then we said the y-intercept was 0, b, so that was that first year when we started, or that starting point, what your tuition was. That's why we had the y-intercept so nicely there. All right, and if time permits, we'll go over some of these.